Today we're solving linear systems by graphing them. So it's going to give us some practice in graphing lines and also in analyzing those graphs. Now, the first thing we have to remember is that when we're graphing a line, for instance, x plus 2y equals 7, the line is the collection of all points that fit that equation. So for instance, when y is 0, x equals 7. I can determine that just by plugging in 0 for y and solving for x. And so the point 7, 0 is a solution to our equation. Another point that would be a solution would be if I plugged in 0 for x and solved for y, and I'd get y equals 3.5. That means that 0, 3.5 is also a solution to our equation. And like we said, the line is the collection of all points that fit that equation, and so we can continue that line endlessly in both directions. Now if I had another line, 3x minus 2y equals 5, and I wanted to graph that equation. Right? I would use a similar method. I would find my x and y intercepts. So if I plug in 0 for x, 3 times 0 is just 0. So that means y equals negative 2.5. That's my y-intercept for my second equation. And if I plug in 0 for y instead of x, (3x equals 5), and so x equals 5 over 3, or 1 2/3 for my x-intercept. So having more than one equation is what we call a system of equations. And the solution of the system of equations is the point where those two lines meet, the point that they have in common. So we're going to estimate that to be approximately the point 3, 2. And we estimate that that point is on both lines, and so it's the solution. But we want to double check and make sure that works. So what we do is we plug in 3, 2 in each equation. The first equation, we plug in 3 for x. We got 2 times 2, and does that equal 7? Yes. And we can try the second equation. 3 times 3 minus 2 times 2, does that equal 5? 9 minus 4 does equal 5. So that point works in both equations, and so it's on both of the lines, so it's a solution to our system of equations. Let's try another one. Negative x plus y equals negative 7, and x plus 4y equals negative 8. So if we find the x-intercept of our first equation, we plug in 0 for y. So take a second, plug in 0 for y, and tell me what you get for x. X is positive 7, so that's our x-intercept. Now, plug in 0 for x instead, and tell me what you get for y. Y is negative 7, so our y-intercept is negative 7. So we have 2 points, which is all we need in order to graph a line. There we go. There's our first line. So let's look at our second line. Let's find our x-intercept by plugging in 0 for y. We get x is -8. And we find our y-intercept by plugging in 0 for x. And we get y is -2. So we got our 2 points. We're going to graph our line. Now, because our points aren't perfect just because of drawing issues, we're going to assume that that's our solution right there for -3. At least we're going to assume that for now. But we're going to confirm that by plugging it into our equations. So we plug in x in the first equation as 4 and -3 for y. Does that equal -7? Yes. The second equation, we plug in 4 for x, -3 for y. Does that equal -8? That's 4 and -12. That does equal -8. So 4 and -3 works in both equations, so that's our solution. Why don't you try one of these on your own? I'll give you two equations. -x plus 2y equals 3, and 2x plus 4y, or plus y equals 4. So pause the video, give those a try, and then when you think you got it, come back and we'll see how you did. So our first equation has an x-intercept of -3. If you plug in 0 for y, you get -x equals 3, so x equals -3. And if we plug in 0 for x, we get y equals 1.5. So it has a y-intercept of 1.5. So there's our first line. Our second line, our x-intercept is 2, because when we plug in 0 for y, we get x equals 2. So there's our x-intercept. And our y-intercept, if we plug in 0 for x, is 4. So the point they have in common is, or the y-intercept of that equation is 0, 4. And when we draw our line, we find the point they have in common appears to be right there at 1, 2. So let's check 1, 2 in both equations. Does -1 plus 2 times 2 equal 3? Yes. Does 2 times 1 plus 2 equal 4? Yes. So that point is correct. That is the intersection, or the solution, of that system of equations. Let's try a word problem. The Parks and Recreation Department in your town offers a season pass for $90. As a season pass holder, you pay $4 per session for tennis. Without the season pass, you pay $13 per session. And they're asking, what system of equations can I use to find the number x of sessions of tennis after which the total cost y with a season pass is the same as the total cost without a season pass? Now this is a common situation when we're going to want to use an intersection of lines, when we're trying to balance two different approaches and find when the costs are the same. So we need to set up our two equations. Well, let's look at the second one first. The second one, our total cost is only dependent on how many sessions we show up for. Since we're not purchasing a season pass, there's no upfront cost. But our rate of change, or our slope, comes from the word per. Okay? So since we're seeing $13 per session, that means we're paying $13 for every x tennis session we show up for. So if x represents our tennis session, we find our total cost by multiplying 13 by the number of sessions we show up for. Our first situation, on the other hand, has an upfront cost of $90, which we're paying regardless of how many times we show up to play tennis. That's our initial cost, or in this case, our y-intercept when we're graphing. But then we're still paying a cost each time we show up. And so if X represents the number of sessions that we play for tennis, then we're paying $4 for each of those. So 4 times X will give us our total cost for tennis, and the plus 90 gives us our total cost for the season pass. So there's our total cost altogether, and we can graph these to solve and find where our cost would be the same. So that's all we had to do, was find our equations. Alright, if you have any questions, feel free to ask. If not, you can get started on your homework.